great conference. I'm really excited to be here. An amazing lineup. For example, Simon's work has also been a big inspiration to what we do in Akka as well. It's borrowed a lot of things from both Haskell and Erlang, and a lot of good stuff out there when sort of designing and building Akka. A lot of from Clojure as well. So it's a big mix of good ideas. At least some of the ideas that I think are good. So I'm the CTO of TypeSafe. TypeSafe is a company behind the Scala programming language, the Akka middleware. We also have a web framework on top, so for doing REST-based MVC style things called Play, the Play web framework. I'm sure you've heard of it. So we try to put together a solid stack, like a full developer experience. But so in this talk today, I'm going to focus on the Akka middleware solely. So without further ado, Akka, actually the name comes from this beautiful mountain up there. I was up there hiking and I saw this light and just realized that I had to go down and build Akka. So I named the language or the runtime after this mountain up in the northern part of Sweden. Pretty good skiing down actually, even though it takes a while to get up there. So where is Akka used? People always ask that. So I'm going to start with a slide showing you some of our production users. And as you can see, if you go through all of these logos, you might recognize some of them at least. Is that it's a lot of diversity. It's a lot of different industries, different domains. I mean, it's telecom, it's e-commerce, it's like gaming, betting, it's routers and stuff like that, and investment banks and all kinds of stuff. But the common theme throughout all of these is that they have this high need for high throughput, low latency, with extreme high levels of SLA, right? So and the third one should not be ignored. I think that's one of the most important things that I think Akka tries to bring to the table is the reliability. If you went to Joe Armstrong's keynote and Rich Hickey's keynote earlier as well, we talked a lot about reliability. And for me, even though I like actors for many different things, and Akka has way more things in its toolbox than just actors, I think that's one of the key things that I think the model enables to write really resilient software. So Akka is the actual core library is fairly small, has fairly small overheads. So people are using it all from Android devices all the way up to like multi-core boxes, all the way up to cloud computing. So Akka can really scale both up and down, which I think are important. And it's a platform that you can use in many different parts of your system. Not just running in a big cloud, but can run it on the client as well. There are efforts now that creating a JavaScript sort of bridge, so you can use parts of it from JavaScript running in the browser on the phones and stuff like that. So there's a lot of interesting things going on there. But one of the things that, if I was to summarize what Akka really tries to do, is manage system overload. I mean, when we have too many users, too many transactions per second that needs to be handled, too much data, too much of anything, that's a really hard problem that most of the applications are facing today. And I think Akka and the ideas that we have there is something that's really up for the job to deal with these problems in an efficient way. So same thing like we're doing at replication, distribution for fault tolerance. So it really gives you a way of programming at a higher level, I think. So what I mean by that is that if you look at it, start looking at it from a concurrency standpoint, right? We all have multi-core phones now and computers, etc. But I think that the default way of doing concurrency in Java, C++, C#, etc. is completely broken. It's the wrong way of abstraction. I think sometimes you actually need to go down to that level. If you're writing operating systems or something, that you really have to work close to the hardware. But I don't think that the hardware semantics and the primitives that the hardware is using to manage memory should leak all the way up into the programming model that we see a lot. So there's a lot of clumping going on, right? And we don't want plumbing. We want to build stuff that's useful for our clients and for customers. So by lifting the abstraction level, we instead program, and when we program with messages in an event-based fashion, all this plumbing becomes workflow, okay? So instead of dealing with these low-level constructs, we think about how do events flow in the system, how do components interact, and since all that is managed by the runtime as lockless, event-based, asynchronous, non-blocking event message passing, you get concurrency, a really good scalability, really good resource utilization as a side effect of that, right? But you don't need to think and architect around that fact, right? So you lift the abstraction level to become workflow. I think, and as I said, I think also on top of that, I think I'm going to talk about later, but I think the actor model has a very superior way of dealing with failure. It has really makes failures first class. Like it's part of your API actually. It's not an exception that you might fail. It's something that will happen, especially if you start running in a distributed environment. And instead of dealing with it as something that's exceptional, you make it like first class in a programming model, and that helps a lot. Another thing that I think is really nice is that actors really shine when you don't know if you need to constrain yourself to a single box, or your application might need to grow across multiple boxes, running in cloud computing, etc. I don't think there should be a distinction between if you want to scale out on multi-core, quad-core, 12-core machine, or if you want to scale out on multiple machines. I mean, they are all driven by the same need. They're all driven by the same demands it's basically just a deployment decision. Should I deploy on a single box? Should I deploy on 4 boxes, on 10, on 100? And that can change as well during the application's lifetime. Sometimes you perhaps need it. For Christmas, you might need around 100 instances on EC2. But you should also be able to like scale down and so on. So I think that's elasticity is very important. And then I don't like a programming model that sort of constrain me in that sense. And Akka tries to do that by sort of embracing the network, embracing the distributed computing at its core, which I believe is message passing. Anything that is synchronous, sort of on the network, and RPC and all the stuff we've seen a long time ago, as attempts to solve that problem are fundamentally broken, because I mean, as long as you use something on another machine, you will send a packet over the network. So it's essentially message passing. And by making message passing the programming model that you use, you're prepared for that world without having to do anything. Then you write your system in a way that you can just take it and start spreading it out to multiple machines if needed. Okay. So you get scale up, multi-core, and out, sort of free as part of the model. So it becomes a deployment artifact. And this is, as I will show you later, it's not visible in the code. It's actually something that you configure, how your topology should look. Okay. So you're going to get all these nice things we talk about in cloud computing, elasticity and dynamicity and fault tolerance and self-healing and all that stuff, right? Also gives you a way of writing extremely loosely coupled model systems. Since all your components have well-defined interfaces, they just completely reactively consume messages and talk to each other. That means that you can easily swap them in and out, and there's really no strong coupling anywhere in the system. Not on subsystem level, not on individual component level either, which I think is a big strength. So how can we achieve this? Yeah, in Akka we use actors, as I said. So what is an actor? It's sort of a try to, in this talk, by the way, I'm talking mainly about concepts. I will show you some code, but trying to explain what the actor thinking, right? An actor is really a different beast, as you will see. It's not a function, it's not an object. It's really something special. So we use it as Akka's unit of code organization, you can say. So we all know this, that the actor helps you write concurrent scalable software. In a way, they look a little bit like JEE servlets or session beans, etc. In the way that you have your code and you have declarative policy decisions that are done outside. Okay, so we don't tangle those things. And as you all know probably as well, it's not a new concept, right? It was first defined in the paper by Carl Hewitt in 1973. It was picked up by Occam, like 83, I think. Erlang picked it up, 84, and so on. So it's really proven technology. It's just in the Java world or on the JVM or in the enterprise in general, except from the Erlang community, I don't think we've really learned to appreciate everything that the actors can give us. So if I now try to take an actor and try to map to something that we know, okay? You can see how an actor can be used in various scenarios. So, in one way, actor can be seen upon as a thread, right? That's sort of a very bad comparison, but in a way, the actor sort of gives you processing that runs on a thread while it's actually doing something. But an actor is not bound to a thread. You can look upon it as a thread while it's executing. It can be an object instance or a component, more coarse-grained component. You can use it as a callback or a listener to something. It's very common. It can be a singleton. It can be a service. It can be a router. It can be a load balancer or a pool. And as we will see, it can, during load, actually transform himself into a router if needed to be able to fan out. And if the load decreases, it can come back to its normal self, etc. It's a little bit like message-driven beans, you can say. But they are in a way, also very different. You can represent an out-of-process service that you talk to. They are very often state machines. So an actor is not really something that we can just map to the Java world or to like a function in Haskell or something like that. It's really something different, and it takes a while to get the feel of like working with actors to appreciate all the benefits of it. So now we're going to take a step back first and see what is the actor model. So the definition of the actor model, according to Carl Hewitt. By the way, this is a great discussion. It's a really fun discussion on channel 9, where Carl Hewitt and Eric Meyer, they're discussing the gist of the actor model. So it's something that I can recommend you to watch if you like. So according to Carl Hewitt, an actor is a fundamental unit of computation that embodies three things: processing, storage, and communication. So processing storage is a little bit like an object, right? But you also have communication as a first-class thing. And when an actor receives a message, we have three different axioms, right? Of things that can happen. When I receive a message, I can either create new actors, I can send messages to actors that I already know, or I can also redefine my behaviors. I can designate how I should treat the next message that arrives. That is something that is fundamental to the actor model. It's called become, right? So if we now look at Akka through the lens of these sort of three core primitives, and I've also added a third one called supervise, because I think that really belongs into the fundamental model of actors. Okay, so if I then start with step 0, define an actor, before we can start looking into the semantics of actually how they behave. So the first thing we do is that we create its public API. This is Scala code, by the way. Akka has Java APIs, Scala APIs. There are also bindings for Clojure and JRuby and some other in Groovy. So you can consume it from. They're more or less feature rich, but basically it runs on a JVM. You can basically consume it from any JVM language if you want. But we support Scala and Java as first-class APIs. Okay. So the first thing you do is you need to create the public API of the actor, and that is the message it can receive. In this case, we create a greeting actor, and just a message who we're supposed to greet. And then we create an actor. And in Scala, actors are classes, right? They're defined as classes. So we say, we create and greet an actor, extend actor. Then we also are now mixing in the logging trait. There's nothing that you have to do, but if you want to get the logging subsystem in, that could be nice. And then we have to do one thing, and that is implement the receive method. The receive method sort of gives you sort of a switch on which messages it should dispatch on, sort of a dispatch table. So here we say, okay, if I get the greeting message here, then I can like peek into it because Scala is pattern matching, so I can just use the destructuring to go in and fetch whatever is inside the object, and I can just greet that guy, hello, and who is the string there. So that's how I can define an actor. Now, if we want to create this actor now, then you should know that actors are extremely lightweight. They are about around 300 bytes. It means I can easily create millions of actors on a single workstation, depending on how much RAM you have, of course. If you add state to the actor, I mean, you have to add to these 300 bytes, but stateless actors are about 300 bytes. And this gives you a way that you can model things that you can't model with threads easily. Since threads has a cap of a few thousand. Right? Actors, they run on a thread pool, as we will see later. That's abstracted by what we call the execution context, or dispatchers. But one thing also worth noticing is that actors, they have extremely strong encapsulation. They have much stronger encapsulation than you have in objects in Java, for example. So they encapsulate state and behavior, but there's really no way for one actor to peek into the state of another actor without using some funky hack right through the reflection or or stuff like that. One limitation of the JVM and one benefit, I'd say, is that we have one big shared heap. In Erlang, every actor have their own heap. So that's good in terms of safety, but it's bad in terms of performance because there's a lot of copying needed to go on. So Akka is really, really fast, but you have to make sure that you always send immutable messages around, like values, that you've probably heard more than once in this talk. Always use immutable values. Okay, but that's if you live within the actor model, then there's really no way you can peek into the state of another actor. The only way you can check what kind of state he is in is by asking him. Okay, and then he might tell you or he might not. Then the third thing that an actor has is a message queue. Right? So each actor has his message queue, and if you want to ask an actor something, just send him a message, and it ends up on his queue, and he's later sort of scheduled to process that message. So now, if we want to create an actor, the first thing we do is we create an actor system. That's sort of the application context, you can say. So we do that. We give it a name. Names are important in Akka. Then we say system actor of, and then we send in the props object. Props object is like the configuration. Here I'm just saying what type it should be, but you can configure a lot of things through this props object. And that maps also well to the configuration files. Everything you can configure there, you can configure in the configuration file as well if you want to do like outside your application. But here also we give it a name, and names are important here. So out here comes an actor. But it doesn't, you don't get the instance here of greeting actor. It's not a greeting actor object that comes out here. Instead, you get a reference to that greeting actor, something called actor ref. And that decoupling is extremely important. First, in terms of safety, right? So you don't have public methods and call that and like bypassing the whole actor model. But even more important, this decoupling enables you to do things like network transparency, like location transparency is a better word. It doesn't matter where this actor is running. It's all configurable. As we can see, here I'm creating this thing, but out here comes a reference, but the instance might actually not run in process here. It might be configured to run on another machine. And that's something that the user of that doesn't have to know. Something that the sysadmin, whoever, like deploys things, decides. So, actor form hierarchies, that's very important. It ties into the failure model. But it also ties into like the way you design and look up actors by name. So each actor system has like a top level guardian actor. Okay? So if you create an actor from the system, then you create a top level actor out of the system guardian. Okay? We name it foo here, as you can see. Then if I then inside this actor use the context instead, what's going to happen then? Then I'm creating a child of this actor. Okay, and so on. So I'm all my actor applications are always trees, always hierarchies. Okay, and for many reasons that we will see, especially when it comes to the failure model. That's very important. But also for naming convention, because as you see, this looks very much like a file system, and we actually query actors and look up actors based on this. So this is /foo. This is /foo/a, and these are actually the names that the actors are given and the way you actually use them. Okay. So the second primitive is send. If I want to send a message to an actor, I'm doing that in an asynchronous, non-blocking fashion. I'm not sending a message to an actor and then I go and sit down by my mailbox and just wait until the mailman comes and give me the response, right? I just send off a message and I go off and do more useful stuff. I might get a reply later, I might not. Depends on the application's behavior, of course. But I never wait. So everything is completely non-blocking and reactive. That also means that it's like fully asynchronous and extremely resource. So we utilize the resources very well. So an actor, if it doesn't receive any messages, it doesn't do anything. It's completely passive. Okay? So in a way, you can say that the messages are like the kinetic energy in the actor system. So if I send off a message, then something's happening with that actor, and he can perhaps start sending messages to his actors, and like behavior starts trickling down. And when everyone's done, it goes down to passive again. Okay? So actors they can have a lot of buffered potential energy, but nothing happens unless someone is told to start triggering, to start acting upon that. So everything's happening extremely lazily, reactively, which I think is very nice. It gives you this very nice event-driven model. We have a primitive we call tell. We also have an alias, just this bang exclamation mark, what's called a bang operator in Erlang, but we call it tell. This is just an alias. You can say greeter.tell and pass in this, or you can just say greeter tell. Scala is sort of flexible in syntax, but it all means the same thing. I'm telling the actor to do something, and I'm returning immediately. What's going to happen is that message ends up on his mailbox, and it will later be processed according to how the scheduler thinks it should be processed. Right? So here's a full example of some running code. Okay? Now, routers is another interesting thing. They are all also, they use for load balancing and stuff like that. So if you want to create a router, you can do it in two different ways. You can do it in code if you know that you will always want to have a router. So then you take some accuracy with router, and then you pass in what kind of router it should be, round robin and the configuration for that, etc. Right? Out here comes a router then. They will spawn up n number of instances. So when the message is sent to him, it will only in a round robin fashion and delegate to all of these. And these can be running on different machines or on the same machine, or that can also change at runtime. You can also add a pool, so the resizer with an upper and lower bound if you want, so on. You can also do this all from the configuration file. So you can, and here you can see, here we use the names again. Foo, bar, and then the child of that, right? So we use names when we configure actors from the outside. That's why names are important. The third one I want to talk about is become. Right? Become is the thing where I can sort of, I can change how I should behave to the next message I receive. And you might ask, why should I use that? It sounds like a very esoteric feature, but it's actually something that when you get into it, you use quite a lot. And you're perhaps more used to that thinking if you come from a functional perspective, right, where you can send functions around and so on. But from objects, when you have static interface, it feels really weird. Because in a way, it's really like If you take a look at it from a type system perspective, it's really like if the actor actually changed type completely. It changed its interface, it changed its implementation. So it will really completely become something different, right? And also these behaviors, they can be stacked or pushed, or compare and swap. That's something you can configure. You do either like push and pop behaviors, so you can go back to where you were, or you can just say, I'm just going to replace it. Okay. So the question is, why would you want to do that? Here are some examples of where I tend to use that. For example, I might have a very highly contended actor that can't keep up with the load. Then it can say, now, okay, I'm out of here. And I just don't have to die. What I can do is I can actually become something else. I can transform myself into a router with a pool with upper and lower bound, for example, and start spinning up instances on other machines if the CPU is churning to becoming too hot on this single box. And when the load goes down, it can like just pop the stack and go back to normal, and of course then first shut down all these actors and then go back to normal. Other examples is one way I've implemented like finite state machines is using this. I might have, for example, an initial behavior that accepts one single message, that is start, for example. And when I do that, I'm becoming running. And when I'm in running state, I might have a lot of messages I can respond to, depending on what I should do for work. One of them might be suspend. When I receive that, I get into a third state, perhaps where I can just receive one message, or act upon one message that is resumed. Then I'm back to running. And one here might be stop, and then I go back to like the dead end. Then I'm sort of evicted and garbage collected, and so on. So, and this makes it very, very clear to implement state machines, because for each behavior, there's no tangling between the different states. Each one is extremely clear, done in its one specific function, and I can also pass state along these. So it's a very nice way to implement state machines. Another example is graceful degradation. I might perhaps don't want to create a whole bunch of routers yet. That would perhaps just add to the problem. I might want to say that the producer should just back off. I might want to start dropping messages. I might want to throw an exception up to my supervisor, telling I'm out of here. I can't deal with this. Or I might want to do something else. And then I can when I'm doing that, I can just transform myself into that behavior that does that. Start throwing exceptions, start dropping messages, or something like that. Start like feeding them into the dead letter actor sync or something like that. Okay. I can also do things like spawning up a whole bunch of empty workers or running on multiple machines, right? And then a master can come in and he can actually start sending out the workers. And then when they're all up there, you can start sending out work. When the work is performed, the result is aggregated back. He doesn't shut them down, but he still pops the stack, so they all become empty. They're still running there for the next master to come in to start throwing his workers out, and like basically pushing up the behavior. So that's a very also nice way of dealing with that. So, I've seen other examples as well. So I think it's a very interesting way. It adds to the dynamic feel of actors. Even though we run them in Scala, or we built them in Scala or Java, they're static, the type languages, they really give you a lot of feel for, like a feeling of being extremely dynamic and loosely coupled, and a lot of things you can do a lot of things that you can't possibly do using static objects and stuff like that. And the way you do it is just to say context.become, and here you pass in your new partial function. And you can also like become that passes state, so you can like actually take your state and pass along into this new closure that's going to do whatever you want. Okay. So how I'm doing on time? Let's see. 20 minutes left, right? So failure recovery. Unfortunately, at a lot of clients during my career, I've seen something like this, right? There's really no way of dealing with failure. Failure is something that shouldn't happen. And if it happens, yeah, okay, we just restart the box or something like that, right? But I think there's a better way of dealing with this. But first, let me start with a rant. I think failure recovery in Java, C, C++, and so on is completely broken. And I think the reason is that you're giving a single thread of control that you do your work in, right? I can just add this. Yeah. So you're giving a single thread of control, right? So that you do your processing in. Now, if something goes wrong, what if you don't have any like failure management mechanisms, like which in Java is try catch? Guess what? You get just a stack trace all the way up to your Java executor service, and there's dead silence. No one knows that something even went wrong. So the only tool you have is to add the failure management right where you do the processing in that single thread. Okay. Which I think has a lot of problems, because it leads to very defensive programming. It leads to programming where the error handling is really tangled with your business logic. If you just look at any Java app, bigger Java app out there, right? You have exception handling all over the place. It's a big mess, right? And I think it's all due to the fact that exceptions don't propagate across threads. There's really no error notification mechanism. It just runs through the stack, and that's it, right? So I think we can do a lot better than this, and that's what actors give you. It gives you like a well-defined mechanism to deal with failure. Okay, it's also sometimes called let it crash. Okay, or embrace failure. But it's really about making failure a first-class citizen in your programming model. It's as important in your actor's or a component's interface as what it can do, right? You might have these methods. You can do A, B, and C, but also the exceptions that are thrown should be part of that sort of interface. It's as likely that something can go wrong as it is that something can go right, and then we need a way to deal with that. So the fourth sort of the primitive that I want to talk about in the actor model is supervision. Okay, and with supervision you get this notification scheme. So you can have one actor observe another actor, and if that actor that is observed, so the child, fails, then a notification will be sent up to his parent, and he can react upon that. And the nice thing is according to the way it's implemented in both Erlang and Akka and a lot of language actor systems, is that it's all declarative. It's not a bunch of code that you write here. Instead, you declaratively say, this is the way I should react to this failure, and this is the way I should react to that failure, and so on. Okay? And this gives you a very clean separation. So the guy that's doing the processing, he's only doing that. He doesn't care about failure. If he dies, he dies. No big deal, because then. So he delegates failure management to his parent. Okay? There's no like tangling or scattering of this. Instead of having this try-catch all over the whole system, you architect your application using an onion, you can say. So the way you do it is that the most important critical state that you can't lose, right? The essence of your application. You put that in the center of the onion, in the onion, and then you sort of that's what we call the error kernel, by the way. It's just a name for it. Okay, that can't fail possibly. If that fails, I'm out basically. But what I do then is that I layer levels of defense around, right? And as soon as I'm supposed to do something dangerous in here, I never do it myself. I spin up another actor, sort of a little minion that I can have run out on the minefield, and if he like blows up, that's fine, right? I can just create another guy and try again. And that minion might say, oh, wait a minute, what is this parent doing? I'm not going to do this. He might actually spin up yet another guy. So in that way you can get layers of defense, and eventually someone has to do the dirty work, right? And he might fail. And then and then we have a declarative mechanism of dealing with that failure. So you get a system that looks something like this, right? Where you push down dangerous work downwards. And so what this means that this guy is a parent for this. He has created him using context actor of. That's all that's needed. Then he's managing this guy here. Okay? Now, if this guy blows up, what's going to happen is that a notification will be sent up, and he can act upon that, perhaps restart this guy and have him try again. Okay? It might be that these actors together implement some sort of service. They might be implicitly coupled. Then the supervisor can say, I'm not, one of them dies, all of them have to go. He restarts all of them, sends notification, you have to restart yourself, and the system can try to continue. Okay? It might be that the guy over here actually doesn't have the sort of the information. It might be above his pay grade, basically, to deal with the error. Then the error is escalated up. Think in the worst case, it might be an out-of-memory error, right? It's not really feasible for any of the layers to deal with that. Then it will be escalated all the way up to the error kernel and dealt with there. What's going to happen then is it's going to blow up. And what's nice then is that actor systems span machines, right? So even if this thing out-of-memory, you get an out-of-memory error here, a notification will be sent across the wire up to this guy, and he will get notifications, see, oh, that whole machine went down. I better do something about that. Because you can never build a reliable system just using one box, right? You need at least 2 or 3 or so. And this might look like a single point of failure, by the way, but it's not, because as we'll see in the last part, when I try to conclude with the Akka clustering, which actually solves this problem. Okay. So by just creating actors like this, context actor, all blah, 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 then I'm becoming the parent of something, of the guy I create. And the default strategy is usually sufficient for a lot of cases, but you can also, of course, create your own sort of strategy, how you should react upon failure, and that is something that we really recommend. The first thing you should do is you should really think through your failures and give them proper types and proper names, right? So not just, if I died, I threw a runtime exception. That's useless. How can you react upon that? It should be very specific names. Well, that's actually I don't have here. So I should change that probably. But that is very important, right? Because I mean, the guy that created him might actually be able to deal with it. But if something gets escalated all the way up to the third layer, it might not be that he's prepared to deal with that error unless he really knows what it's all about. But we have this little DSL. So you can say, I want to supervise a strategy. In case I get an arithmetic exception, I want to resume. If I get a null pointer, for example, I want to restart the actor. If I get something else, I want to escalate up to my parent, and so on. And there are more directives and more things to this, but this gives you the idea. You can also say things, I'm not going to accept more than 10 number retries within 1 minute, for example, and something's really wrong, right? Then I'm just, the external service I'm depending on might not be there. That's why I'm just failing. There's no use doing that. Then I can react differently upon that, and so on. So the full example here is that I override the supervisor strategy here, and I create my actors using the context. Then I become the parent, and then I can use him. And if he fails, I get a notification, and I'm dealing with the error according to the way I have declared it. Okay. And from the supervised actor's perspective, there's a bunch of callbacks that will be called, right? One be when the actor is started, like post-start, pre-start, post-stop, and all these. Also pre-restart, post-restart. If the supervisor has to kill the guy, that thing will be called, pre-restart will be called right before, so he can clean up resources. And post-restart will be called right after. He can reinitialize himself, open up a socket or whatever he was doing, right? So now going over to remoting. So this was like Akka. If you don't feed this with any configuration file, all run in process, right? But now you can take everything I've showed you so far and make it remotely available by feeding it a specific configuration file. So the only thing we need to do is say, for this greeter actor, for example, /greeter, that's the name of the actor. We say, I want that to be remote, and I want it to be instantiated using the Akka protocol. That's our default protocol. We also have a cluster protocol that we'll talk about just in a second. And you can say, okay, I want it to be running on my system. That can be an IP address or a DNS resolvable host name. No, sorry, this is the actor system. Sorry, this machine is the IP address or the host name. And now it runs on this port, for example. What's going to happen now is whenever that guy is created, he will be created here, right? And every guy that asks for him will get a reference to the guy running here. Okay, so it's really no code changes at all. Okay, remote lookup looks like this as well. You can say, okay, I want the Akka protocol, the actor running on my system and on this host, blah, blah, blah. And the user is actually the user space because we have different spaces. We have system space and dead letters and all kinds of stuff. So this looks all good. No, it doesn't actually. This actually is not as optimal, right? Why? Because we have fixed addresses. Like even though it's outside in the configuration file here, when we do lookup, we actually have to know where the guy is, right? And that's where we solve with Akka cluster that's coming now in Akka 2.1 that's going to ship in a week. Okay, so what we add there is first cluster membership, so you can just add nodes on the fly. You get the elasticity, so you will get notifications when nodes come and leave. And we have a whole bunch of features that take automatic advantage of that. We also have leader determination. I was saying determination because there's really no election process going on. It can always be statically determined by every node in the cluster who the leader is. But it's really what we call leader election in the, whatever, zookeeper or whatever you use, right? We have a failure detector. And using these things, we implement things like cluster death watch, for example. You can monitor other actors. Supervision works across machines. Even if a machine goes down, etc., like this. We also have cluster-aware routers. So you can define a router to start taking advantage of the cluster. I want to show you how just in a second. So the only thing you need to do to enable clustering is to say, I want to load the cluster extension, and then I have, we don't use multicast, by the way. So we need to have an entry point into the cluster. So we adopted the same scheme as you have with Cassandra, that you have the seed nodes, right? We perhaps later do a multicast version, but multicast doesn't work on EC2 and cloud environments where a lot of our clients run our stuff. So you need some contact points, basically. That's the only thing you need. And these nodes just take that role in the initial handshake, and then there's nothing special about them, right? So you really get this fully peer-to-peer masterless system, in which you can actually point to a leader if you have something that needs to be done by a specific leader. Some systems need that, but that's basically it. Everything is completely masterless. And now, if you want to take advantage of this, for example, in the routing, you remember that we could configure a router like this, for example, say consistent hash and blah blah blah, and then we can just add this thing here. I'm saying now it should be cluster router. And then I can say, for example, I want to run around this whole bunch of configuration things here, but this shows you that you will allow to run routers on the local machine, mean the guy that actually using the routers, have the router reference. And you can say I want max number of instances, like 3 on the node. You can also say that I want maximum 100 instances here. And what means by that is that if I have 3 nodes, I will run 9 actors, right? But I will continue to spawn up 3 new actors, routees, per node that joins until I reach the cap maximum 100. And there are different ways you can slice the cake as well. But the nice thing is that the routers are cluster aware. So when you add new nodes, they will start using them. Remove the nodes, they will move over to the current running hosts, etc., and stuff like that. Another thing that I can also mention is that we also have the typeset console. It's actually currently just the Akka console, but we'll add support for other stuff like play later. But it's a really good way of introspecting things, and we use this a lot when we're developing Akka. You can get like visibility on the node level. You can see the full system overview. You can zoom in on a specific dispatcher, and zoom in on specific actors and see like mailbox size and throughput and stuff like that. So that's pretty nice. If you want to try it right now, you can just go to console-demo.typesafe.com to see it in action. So that was basically what I had in mind talking about. I could give you some, either we take a few questions, or I can give you what the next steps with the clustering is. I don't know, it's up to you. But I just want to conclude by saying that Akka is much, much more. It has a lot of different things. For example, we interact with the Scala STM. software transactional memory, so you can get transactional actors. You can really compose transactional message flows and then have full message flows like rollback. We have data flow concurrency. We have agents that's almost one-to-ones, completely stolen from Clojure. You can say they have the same semantics, which is also a very nice way of dealing with concurrency. More functional, in which you need to send the function to the state instead of sending state to the behavior in a way, so it inverts that a little bit. Really nice. CRMQ integration, with Camel integration, we have MQP integration. We have already implemented an event bus that you can use, right, from pub/sub on that, and we have abstracted a lot of things that you need to do in patterns. So we have a pretty nice patterns catalog for more reliability, durable mailboxes for durability, etc. So if you want to learn more, you can go to akka.io. This is our blog, our team blog. There's a lot of nice material there. We had a summer of blog where a lot of people that were using Akka wrote blogs over the summer. And if you want to know more about typeset, go to typeset.com. So that was basically everything I had in mind of covering. So there are 4 minutes. So either we take a few questions, or I can just give you like a glimpse of what we're working on right now. I don't know what you prefer.
Questions?
Any questions? Yeah. Pardon me? The thing is that we provide an API in which you can plug in. We sort of abstracted the mailbox into an interface, and we have tried to abstract it as much as possible, so you do all the heavy lifting, but you have to plug in an implementation. We provide one single implementation that is a file-based, so transaction log on disk, and that's on the disk, on the machine that the actor runs on, right? We used to actually have many more durable mailboxes for all kinds of NoSQL databases and stuff like that, but since we're a commercial company, it became really hard to support all of these. So we actually lifted them out. But there are a lot of community-created ones. The latest one was a guy doing a durable mailbox based on AQP, for example, Rabbit. So it's very easy to do. It's just a few lines of code, actually, to plug in your own. But we provide a sort of file-based one as a reference.
So that means for recoverable messaging, so if we put an Akka instance in messages for another one actually down, can you physically redeliver the message back up again?
Yeah, I mean, the guarantees of the actual durable mailbox is up to the back end, right? But we have a bunch of patterns that tries to build things like building blocks around that. For example, we have peek and pop pattern. For example, you can first peek it, and if you successfully execute it, then you can pop the message. We also have something called the reliable proxy that tries to do redelivery if the network goes down, and so on. But since all of these things has a cost, and sometimes a very, very high cost, we try to provide, I mean, the raw things with Akka, right? The thing, so the common denominator, you can say, provide really, really fast message delivery. And all the guarantees that you might need, you can plug in through modules or through patterns that we have, right? So that's our sort of design philosophy. People might ask, why don't you do guaranteed delivery on default? And that's really, I mean, then I ask, yeah, well, what do you want? Most ones and only ones, and all have different guarantees, right? And honestly, I don't believe there's anything like guaranteed delivery, right? Because an actor might shut himself down before the message is even received, right? I mean, it ties into semantics of the application even, so it's really hard to guarantee something like that. Generically, it's very much in the hands of the application developer, which we try to help, as I said, with tools and patterns and stuff like that. Yeah.
Can you talk about the pattern you recommend by the stateful actor? Let's say if I'm a state and it goes down really fast. And so keeping it all together is not enough.
Yeah.
So you talk a little bit about that, and what seems to be problematic,
Yeah. This is sort of tricky because he might actually fail just because he was in the state that he was here, right? So it's not that easy that you should just reinitialize the state he was in. Sometimes that's the right answer, sometimes it's not. But since we have these callbacks, right, that allow you to, that actually take the exception, we allow you to actually, once the things fail, you like pass the state or the context up to the supervisor, and that will be passed in, and he can reinitialize himself with the same state, right? Or he can be, right before he's killed, he can store away his state in the database and read it up, or to a buddy somewhere, and then ask for it again. There are many ways, but it's hard to say that that's a good idea, right? Because he probably failed for a reason, and that might very much differ. So that's why the default is just to kill the actor and have him sort of restart himself into the initial state. And then if he needs something more, he needs to go out and fetch it and so on. But that's just a default. You can slice it, the problem in any way you want, really. So I've seen all of the approaches that I've just mentioned. I've seen in practice. And yeah, that is depends on the exception, right? If there's a hardware failure, those usually extends error, right? So then you just need to make sure that you take account for that. But the default is just terminate, is escalate all the way up and terminate the actor system on error. So unless you do anything specific, it's going to terminate.
Okay, we wind up there. Thank you very much.
Thank you.